all the participants, and welcome you all for the last day of this Friday's FDP. I welcome our resource person, Dr. Rajeshwari Madam. Madam, welcome.
Thank you. Yes. Yanambal Madam, thank you. Thanks for the invitation. Thank you.
Thank you for accepting our invitation and to deliver the lecture today.
Good morning to one and all present here. This is the first session of last day. This is the fifth day of our Atal FTP. A warm welcome to our today's resource person, Dr. R. Rajeshwari, Professor from Jubilee Department, Government College of Technology, Coimbatore. Now I introduce our resource person, today's resource person. She completed her BE in 1995 at Tyagaraja College of Engineering, Madurai, and completed her MD in 1998 at Tyagaraja College of Engineering, Madurai. She completed her PhD in 2009 under Anna University, Chennai. Her area of specialization is power system engineering and soft computing techniques. Now she guided more 13 PhD scholars. Now she is guiding 5 candidates, PhD scholars. So her publications are international journals are 60 numbers and national journals are 3 numbers. She delivered guest lectures more than 50 plus in the field of researching domain. She is now a reviewer in IEEE, IET, Elsevier journals. She did 3 TechU sponsored projects worth rupees 50,000, rupees 1.5 lakhs and rupees 3.5 lakhs. I welcome you, ma'am, once again. Now I hand over the session to our resource person, Dr. R. Rajeshwari, ma'am. Please, ma'am.
Thank you, Vimala, madam. Thank you. Thanks for welcoming address. And shall I start presenting my screen, madam? So is it audible? Is it?
Yes, ma'am. It's clear.
Is it displayed, ma'am? Is it displayed, ma'am?
Yes, ma'am.
PPT? Okay.
Your screen is visible.
Yeah. Thank you so much. Good morning to one and all present online. So first of all, I would like to thank the organizer for giving me this opportunity in delivering lecture on this particular topic, protection of a smart grid using synchrophasor technology. And I would like to thank organizer and KLN management for giving me this opportunity. And I feel very happy in joining this Atal FDP 2020 conducted by IEEE Department of KLN College of Engineering. So to be part of this particular program, so I feel very happy. And so the topic allotted to me is about synchrophasor technology. I think, madam, screen is visible?
Yeah, visible, ma'am, visible. It's visible.
Actually, it looks like a flickering in my laptop, madam. That's why I'm asking.
There is no
I'm observing some flickering on my screen. That's why I'm asking.
No, ma'am. No.
It's continuous, ma'am.
It's clear.
It's clear. Okay, thank you all. Okay, so about synchrophasor technology, my outline of this presentation is about motivation for synchrophasor technology, then synchrophasor fundamentals, and then we will apply the synchrophasor technology for protection problem of power system. So this is more towards electrical domain, EEE domain. So actually, I divided my presentation into this segments because to enter into the last segment, you should know about some of fundamentals about synchrophasor technology. And before that, you should know what is actually motivating me to enter or to follow the synchrophasor technology for power system. And actually, the synchrophasor technology is being used for all of activities. That is, all of activities means power system, you know, our power network is a very, very large network. So to operate our network, power system network, we need to perform certain operations or operational activities and control activities, right? So this is possible. This operational and control activities are all possible only when the system is being properly monitored, right? And to meet the operational constraints, the system need to be operated reliably, and also with respect to quality point of view, the quality of the system, that is quality of the supply. The quality of supply should be maintained, right? So quality and reliability are the two main concepts or aspects to be followed when you are running or operating a power network. So operational activities, certain operational activities and control activities will be performed, should be performed in a reliable fashion. And also reliability, when we talk about reliability, the system should be protected against any kind of abnormalities. So protection, that is operation, control, protection, and monitoring. So all these activities are all very, very essential. So actually, our conventional power grid is being operated with doing all such activities, but with a conventional way. But this synchrophasor, when we talk about the synchrophasor technology, this is playing a role in all of these divisions of this work. It is operation, control, protection, and monitoring. So, my part is about concentrating or focusing on the power system protection part. So before entering into the application of the synchrophasor technology for protection purpose, so first let me tell about the motivation. That is, from the first part, what is, you could understand about what is synchrophasor technology all about, and why do we need synchrophasor technology, and then what special things it provides us that the previous technology couldn't. So these are the essence that could be derived from the discussion of the first topic, motivation. So we'll move on to this motivation of synchrophasor technology. So we have power system, right? A structured power system. Now the structured power system is being disturbed. It has been converted into deregulated one, but we have the connected network, the system, power system. So the operational paradigm of our power system is going like this. That is, from the existing power system, with the help of CT, PT are being used for sensing voltage and current signal from various points of power system network. So with SCADA technology, that is, you know, SCADA is nothing but supervisory control and data acquisition system. So with the help of that technology, our existing system is being sensed. That is being sensed in the sense the parameters, the electrical parameters of the system is completely being communicated to the EMS. So to the control center, it is actually communicating the data about the power system to the control center. So the control center is actually equipped with EMS software, energy management software. So energy management software, it is nothing but about running of certain programs. That is operational activity. When we consider operational activity, you know, they are nothing but load forecasting, economic dispatch, unit commitment, and then economic dispatch. So these are all operational activity, right? You know, to operate our network, it is necessary to consider, that is, the operator need to consider the balancing in the generation and the load demand, right? So The operational constraint is making power balance. We call it as power balance, right? So instant to instant or time to time, this power balance needs to be maintained by our network, right? So this is being performed with the help of these activities. That is, continuously have to monitor the load demand or expected demand to be satisfied by the network with available or new running generators, right? So generation and the load need to be balanced. So this is about operational activity, and this is actually being done through these three different activities like load forecasting, unit commitment, and then economic dispatch. And the control activities are nothing but to maintain the quality, of the supply at the customer point, at the customer or consumer point. This voltage and frequency, we are very particular about the voltage supply to the consumer end and the frequency. So these two variables are these two variables needs to be maintained at their nominal value. Otherwise, the appliances or the demand or load will not perform to its satisfied level. So it is necessary to maintain these parameters within tolerable limit. Therefore, control action needs to be performed by running this EMS software at the control center. So the control center people will give the control actions to be performed at the respective points of the power system. So this is how our power system is operating. Okay, so with this knowledge, we'll move on to the traditional measurement and monitoring system, existing measurement and monitoring system. So as I said earlier, this is SCADA based. Our existing system is purely based on the SCADA, that's sensing and communicating the data or information about our power network to the control center is being performed with the help of the SCADA. That is supervisory control and data acquisition system. So from the yard, the SCADA means what? SCADA technology or the SCADA network is actually software is acquiring the analog signal. Acquiring analog signal in the sense from CTPT, which are connected at the point where we want to track the information. So from CTPT, analog signals are being acquired from the remote terminal unit, which are connected at that particular point. So the SCADA is actually giving the data to the EMS, right? So the main thing here is about how fast the data goes to EMS from the SCADA. That is the question. Actually, the SCADA existing technology, is giving data at the rate of once in 4 to 6 seconds. That is, output data rate of SCADA is only about 4 to, that is once in 4 to 6 seconds, in the sense the parameter is being communicated to EMS once in 4 to 6 seconds. And that too, the values are all declared in RMS. Root mean square value are being conveyed to the EMS, right? So this is one of the main problem, because once in 4 to 6 seconds, in the sense, the cycle time, about our frequency of operation, it is 50 Hertz, 20 milliseconds. Cycle time is 20 milliseconds. So in 4 seconds, that is in 1 second, 50 cycles are being completed. So even in 1 second, many things could have happened to our network, right? So in 20 milliseconds, there may be some changes, or the changes, I'm meaning the disturbance. So lots of disturbances could occur in the signal. So the signal captured by the SCADA technology is only one time in 4 to 6 seconds, means it is not focusing or it is not sure about the presence of dynamics. Dynamics are transients present in the system. Our SCADA system is not sure about the presence of oscillations. So here we need to get data about that network at a much faster rate. So the first shortcoming of this existing technology is what? This one, right? So we go for a new measurement and monitoring technology. Actually, to stress or to support what I'm saying here is it has been shown with one plot. You can view this plot. This is voltage disturbance being recorded on April 5th, 2011 by US Grid. So it is actually showing both of the measurements, SCADA measurement and one of advanced measurement. Okay, I'm letting that other measurement which is being represented by red in color. I'm just saying that has been performed by some other new technology. Let it be black box. So that black box is giving perfect, whereas we are considering that as a reference here, a standard one. So this blue color that represents the SCADA measurement. The voltage has been measured by SCADA technology. So if you look at this blue color, it is more or less, that is it is more or less constant. It is more or less constant, or it is like a straight, it is a line. It is a line. It is not showing any variations, any deviations or oscillations of this voltage. So the power system dynamics, that is to capture the power system. You know, our power system network is not a steady state. It's not a steady state network. It's it is subjected to many of the troubles or disturbances, and so lots and lots of dynamics are happening at various points of the network. So it is necessary to monitor the dynamics. So to capture power system dynamics, we need to increase the rate at which the data being captured, right? See, this is actually required for analyzing the disturbances. Usually, earlier we are when we have a disturbance like a blackout or brownout. So for all happenings or disturbance happen onto the network, usually or earlier, power system operator will be doing some post-mortem analysis, because SCADA is giving only what? The data once in 4 to 6 seconds. Therefore, with the help of the acquired data, they are actually get into this kind of analysis to get the reason or to analyze about the reason for such happenings, right? So that kind of post-mortem analysis or post-disturbance and analyzing the existing disturbances, it is necessary to capture the data at faster rate. Okay, and also about talking about the control actions. So about the operational paradigm of our power system, we talked about the control action. So this control action is being conveyed by the control center to the respective point of the power network. So if suppose data is being captured at this particular rate and doing some work, that is doing some work in the sense execution of program at the control center and conveying to, so there is of course the communication delay would be there. So capturing data at some point and delivering some control action to the respective point is at some other point, some other time. So that control action may be suitable or may not be suitable for that present situation. So that is another problem. That is another problem with this existing technology. Okay, so actually the measurement is actual measurement of the voltage fluctuation or voltage variation around the nominal value in per unit is being shown by this the new measurement technology, so which is shown in red in color. Okay, so you can compare these two plots. So SCADA is only focusing the steady state value. It's not focusing the dynamic value. And one more thing, the synchronization of the data captured. So we need to synchronize the time or synchronize the data captured at various points of our network. So this will give an accurate view of entire power system. Because see, to stress my point, again you can refer this plot. See, this plot is actually giving tripping data, the tripping data of this G1 and G2, where G1 and G2 are nothing but generators present in the power network and one of line. So red color indicates the line tripping, or the dip in power in the line is being measured, and it is actually conveyed to the center only after some time. You can look at the time scale. This G1 and G2 are the two generators which are tripped at the same time and conveyed to the center at the same time. See, look at the seconds. So the seconds at which these G1 and G2, these events happened earlier. That is, earlier it has been conveyed to the center, whereas the dip in power in the line being conveyed at several seconds later. See here, 15 seconds, 20 seconds. So between 15 and 20 seconds only, it has been conveyed to the center. So look at this. There is some difference in time of conveying the message, right? So this is again, this is called a time lack of synchronization. So the data measured, the data given to the center, which is actually doing some action, that is execution of program, operational activity program or control activity program. So to do that program or executing that program, it is necessary to get synchronized data, time synchronized, especially time synchronized data. So the measurement needs, because our network is connected one, our wide area network, I'm using the word wide area network. You know, our network is being converted to a single, that is Indian grid is a very big network. It is one among that is very large network, very large power grid in the world, right? So because earlier we had 5 different regional grids, that is before 1991. So now we have single grid, one nation, and operating at one frequency, 50 Hertz frequency, right? And we are using one more word, one price, single price for per unit, right? So such a large network we have, and that network needs to be, that is the measurements have to be happen at various points of the network, need to be carried out at the same time. That is called time synchronization. So the measurement needs to be performed at the same time, in the sense what we call it as time synchronized data are available. Okay. Next important thing is about, see, the bus voltage angle data is required as a measurement. That is data. What is angle data? See, if you look at, grids, power grids are all interconnected. If you consider our Indian grid, 5 different regional grids are being interconnected through HVAC and HVDC lines. They are nothing but tie lines, and they are managed by Power Grid Corporation India Limited. So these lines, several lines are there. For example, our southern regional grid is being connected with the remaining new grid. We call new grid, NEW grid, which is nothing but the other 4 grids, connected grid, other 4 regional connected grid. So that new grid being connected with the southern regional grid through near about 11 number of tie lines, right? So the 2 areas, you can consider these 2 grids as 2 areas. So 2 areas can be considered as 2 buses. So if you look at this, look at here. So 2 buses are there. two buses. You can consider these as two areas, two different areas which are connected through transmission line. So this area is operating at, this is being operating with voltage of V1 phi1, and this area is operating at V2 phi2. They are interconnected. So interconnected in the sense two areas are operating at same, needs to be synchronized first of all. You know about synchronization. So synchronization is a big headache because we need to maintain same frequency, same phase sequence, then same phase magnitude. All of the phases should maintain same magnitude of voltage, right? So all such parameters needs to be satisfied to make this connection, to make this interconnection, right? So when you are interconnecting these two different areas, meaning that they are connected at same, the voltage must be same, that is V1, V2 must be maintained at some constant value. Then this, if suppose this power transfer, actually interconnection, you know the reason for getting into this interconnection, it is for exchanging power, right? So the more power, excess power from the surplus area may be transported to the deficit area, right? So power exchange is possible. Power exchange is possible with the help of this interconnection. So this is one of the advantages. There are so many advantages in having this interconnection. So if suppose these two voltages at these two buses are maintained at different are maintained at voltage, certain voltage, constant voltage, and if suppose the power transfer from first bus to the second bus. So, you know, the power transfer, real power transfer can be expressed if suppose the voltages are being expressed in phasor form. This power transfer from first node to second node is nothing but V1, V2 sine phi1 minus phi2 by XL. XL is the reactance of the line, which is interconnecting these two areas. So V1, V2 and XL are all constant in the sense, then power transfer from one area to another area is being decided by here, this phi1 and phi2. So what are this phi1 and phi2? They are nothing but the power, the phase angle of the voltage. Phase angle of the voltage. So keeping these two voltages V1 and V2 constant, and during lay down of this particular installation of this particular transmission line itself, this XL value been decided. So XL is again a constant. So V1, V2 by XL are all constant. Therefore, the power transfer from one end to another end is decided by this phase angle. This phase angle. So the power transfer, that is actually a problem, big headache here when you are making interconnection. This power transfer should be in a controlled fashion. Okay, so the power transfer from one end, surplus area to deficit area, should be with respect to the rules and regulations, right? So they should follow, otherwise it is called as a power theft. It is called the power theft, right? So, but when we have this kind of connection, there would be, naturally there would be power transfer with respect to this change in phase angle. This change in phase angle. If suppose phi1 is greater than phi2, phi1 is greater than phi2, there would be power transfer from this first node to second node. So if phi2 is greater than phi1, then power transfer from the second node to first node. Power flow, power transfer would be reversed. So the power transfer is actually governed by these angles. What are these angles? They are nothing but voltage phase angles. So these phase angles are actually deciding the power flow through the line. This power flow is actually giving a stress. If suppose this is controlled or knowingly it is being transferred in the sense, then that is okay. Unknowingly, if there is power transfer in the sense, then that will give a stress at these buses. So you might be heard about one of famous blackout happened in the year 2003. That was happened in the USA network. See, actually there in that power blackout, they analyzed So during that period, they haven't employed the new technology, synchrophasor technology, but without that, but with the existing technology, they gathered the data and they did post-mortem analysis. And the post-mortem analysis, in the sense, they just run several runs for runs of load flow analysis with available data. You know, conducting load flow analysis will give the state of the system. So what are the states? They are nothing but voltage in phasor form or rectangular form. That's it. So the voltages at various points, I'm referring this various points are nothing but buses. So bus voltages are being calculated through conducting load flow analysis, right? So several counts of load flow analysis being done, and they extracted the information about the system. They just divided the complete network into two areas. So one area with a bus of Cleveland, with a bus named as Cleveland. Cleveland is nothing but a city name. And West Michigan. So Cleveland and West Michigan buses, they divided into two areas, and they did load flow analysis. And with the help of load flow analysis, they extracted information of this phase angle, bus phase angle. And this phase angle is being plotted from certain time to certain time, means just time very before to the blackout happened. So it has been these two values, that is a phase angle at Cleveland bus and the West Michigan bus. West Michigan bus is blue color. This blue color plot is representing the phase angle variation, which was measured at West Michigan, and this red color indicates the phase angle variation measured at this Cleveland. So this phase angle, if you look at this variation of this phase angle deviation, it is actually maintaining before this particular time. So this is about actually around 10 minutes only. So before this angle, it goes on increasing as time progress, and at the time of blackout, the angular deviation between these two buses was around 10. That is, it went beyond 100 degrees. So it's suppose the operator is being provided with this indicator. If the operator is being provided with this indicator in the sense, this phase angle deviation is being observed by the operator in the sense, well ahead, it can be, this blackout can be what? Avoided. It can be avoided, right? So this phase angle we call this as a key indicator of system stress. It indicates the system stress, right? So it is necessary to measure this phase angle in, or this voltage in phasor form. Okay. So what is actually motivating us to get into the new technology? The new technology, we need to get into a new technology which is supplying this information, this key indicator. Yes. Key indicator, and then time synchronized data. That is data from the power system. It should be of time synchronized. And one more thing is what? One more thing is faster rate. We need to acquire the data at faster rate. That is in a cycle, at least once in a cycle. So these three are very, very essential to monitor our network perfectly. Okay. Next we will enter into the synchrophasor fundamental. So synchrophasor. So we talked about the phasor representation. So phasor is not enough to represent this particular technology because we need synchrophasor. That is phasor 2. You might be heard about the word phasor, but hereafter in our electrical network, we will be referring, as far as our power system network is concerned, we will be referring synchrophasor, because we need to get this phasor information at various points of the network in time synchronized manner, right? Actually, this phasor concept has been introduced by Charles Steinmetz in the year 1893, and that has been followed by Dr. Arun G. Phadke. He is an Indian, and joined with Dr. James S. Tharp, and they both worked at Virginia Tech, USA. University, Virginia Tech is an university. So there they have started working. They used this concept, and they used it for the estimation of real-time phasor measurement. So they used, with the help of this GPS satellite, they generated some time reference. So absolute time reference is required for getting this synchronized measurement, this property. So they developed firstly in the year 1988 one of phasor measurement unit with the help of this GPS satellite. And first commercially available PMU was manufactured by Macrodyne company in the year 1990s. And as of July 2014, 1,300 number of PMUs have been deployed in US grid. And in India, we are using, that is by the year 2016, we are using 1,652. 1,652 number of PMUs are being employed in our Indian grid as of now. So what is phasor? We are talking about phasor, right? So phasor is nothing but a rotating vector. You know about vector having magnitude and the direction. We call it as vector. When a quantity, physical quantity, is having magnitude and direction, so that can be represented by a vector. So, but here alternating quantity, our voltage and current are alternating quantity. So alternating quantity can be represented by phasor. Phasor is nothing but rotating vector. You know, it is rotating at this vector. This vector is rotating at a speed of omega, angular velocity of omega, where omega is 2 pi f. So for 50 hertz operation, 2 pi 50, right? So the angle sweeps 18 degree in 1 milliseconds because the cycle time is 20 milliseconds here, right? So what is the synchrophasor? It's a definition. We'll look into the definition. Synchrophasor, it's nothing but synchronized phasor. So we are focusing, that is, the phasor needs to be measured at a synchronized way, that is time synchronized. So we have number of buses in our network. So if we are performing measurement at various buses of the network, this measurement needs to be done in a synchronized way. So they must be time synchronized, right? So synchronized, synchrophasor, it's nothing but synchronized phasor. So what is this phasor? You know, the phasor, alternating quantity, the phasor or vector, it's this rotating vector, its magnitude, it's nothing but RMS value. So RMS value, it's nothing but peak divided by √2 would be the RMS value, and we are letting this RMS value as the magnitude of this rotating vector. And the phase angle of this vector is phi, where this phi is nothing but angle between the peak of the alternating signal, that is the angle between the peak and the time reference axis. What is this time reference axis? See, this time reference axis actually been received from GPS. So which is actually initiating the time synchronization, which has been used for getting time synchronization. So 1 pulse per second signal is being received from GPS, global positioning system, satellite system, for getting this property, time synchronization property. So once it is received, if suppose the PMU, that is PMU, or not PMU, a box which is measuring this phasor, a box which is measuring the phasor, if it is receiving 1 pulse per second from this GPS system, and that can be considered, that signal being considered as a reference. With respect to this reference, the angle, phase angle is being measured here. So A angle phi is the phasor representation of this alternating quantity. So see, in this is the synchrophasor, A angle with angle phi, right? So this is known as phasor conversion. So alternating quantity can be converted into phasor quantity, and that too, if you are giving a time, if you are giving the time stamping is nothing but the time at which the signal is being measured, or this signal is being measured in the sense phasor is being declared. So along with this time stamping, we call it as synchrophasor, time stamped synchrophasor value of this alternating quantity. Okay, so how do we represent the synchrophasor? As you all know, this can take any of the form, polar form or rectangular form. So A angle phi, or A plus, that is A real part, plus J imaginary part. So both form of representation can be used in this technology, synchrophasor technology. Okay, so this is about representation. Okay, so what is this PMU, phasor measurement? So far we talked about the word phasor, and we need to measure this phasor at various points of the network. And this is being performed by an instrument called a phasor measurement unit. That is the instrument which measures phasor. We call it as phasor means what? We already discussed that it requires the GPS signal to give time reference, right? So it should have GPS accessibility, right? So a device, we define this PMU as a device that produces synchronized phasor frequency and rate of change of frequency estimates from voltage and current signals and a time synchronizing signal. So from the inputs of voltage, current signal and a time synchronizing signal which is received from the GPS. So suppose the unit is delivering synchronized phasor of voltage and current, then frequency and rate of change of frequency, we simply call that device as PMU, phasor measurement unit. So what is actually inside in this PMU? So PMU comprising of a processor, a simple processor. It will have just GPS antenna, receiver would be there. So GPS receiver would be there. So that receiver will be receiving periodically the reference signal, that is 1 pulse per second. And with respect to that 1 pulse, receiving of this 1 pulse per second will be having, that is will be initiating the sampling process of the acquired of the input voltage and current signal, right? And the cycle data or the window in the sense the data acquired for in a window, one window. So that window length maybe of a cycle time 20 milliseconds. So for each 20 milliseconds, number of samples would be sampled, and those samples and that one window of or one cycle of data being fed as input to the processor, and the processor will be converting, will do some process. You know, DFT is one of the mathematical tool. Is a tool which converts the sampled sequence or the sequence of samples into what? The phasor form. So the processor would be programmed to convert the sampled signal into the phasor form. So phasor form is being generated by the processor, and it is being conveyed. Actually, the processor is being provided with a program to calculate the frequency, to capture the frequency, voltage, current, sequence components. That is positive, negative, and zero sequence components. Once, if voltage and current phasors, all the three phasors are being measured in phasor form, and it is very easy to convert it to the sequence components. So sequence components can be easily determined, then frequency, rate of change of frequency, and also the circuit breaker status with the help of this voltage and current acquired. Because they are the input. Those are the input to the PMU, right? So these are the outputs. These are the outputs, right? And reporting rate, if you look at the data rates, frames per second. See here for 50 hertz, we went up to 50, even 50. 50 number of frames per second can be acquired by the existing PMU, market available PMU. And for 60 hertz operation, even 60. So 60 means what? 60 number of, that is each and every cycles are being captured. That is the meaning. So data rate of this PMU is very, very at a higher, faster rate. Okay. So where can this PMUs be integrated in the power system measurement infrastructure? So the point at which we need this measurement, this kind of measurement, that is especially been provided at a bus, that is substation. Substations are all now equipped with substation with higher voltage rating are all being equipped with this PMU. So there the CTPT, the output of CTPT are being fed to the PMU. So CTPT output are all nothing but analog signal, voltage and current signal, where this PMU is being is having link with the GPS system. So through antenna, it will receive the time reference signal, and so will start measuring, and also for the measured phasor, that will give this time stamping also. So time stamping is nothing but the time at which the measurement has happened. So that also been what appended and then transmitted and then giving the output. So this voltage and current are given in phasor form. Okay, so this is how this PMU are integrated, and how are this PMUs been time synchronized. So this is actually possible with the help of available GPS system. So you know this GPS system, it is there is around 32 number of satellites orbiting around the Earth. So this is free of, this is been provided by US Department of Defense, provided at free of cost. And if suppose one substation is being provided with this particular equipment, this PMU, that antenna, so that location being identified by minimum at least 4 satellites are needed. So we'll be locating one particular antenna, and similarly the substation too, right? So the satellite is actually giving a pulse per second, and that pulse per second is being used as a time reference here. And if suppose, and with respect to that time reference, measurement is being performed at this particular bus. So the measurement would be A1 angle phi1 for that particular substation 1. And similarly, the same structure is being used at other substation also. Therefore, the measurement performed by this PMU would be giving the form of A2 angle phi2. Phi2 is the phase angle of the voltage at that particular substation. So substation are nothing but bus in the system, right? So this is how, so at the same time it has been given, and the time is actually the time of reference for both of the substations are received from the same system. So the time of measuring the synchrophasor or synchrophasor measurement is being performed at the same time. So that is actually giving what? The time synchronization. Okay. And the performance, there are 2 performance classes of PMU. This is about types of PMU. That is, we have in market, we have a P class PMU and a M class PMU. See, this P class PMU are meant for protection and control purpose. Whereas M class PMU are particularly meant for monitoring purpose. Okay, so P class, as it is requiring faster response, it requires faster response, so it doesn't bother about the high frequency. That is, its operation relies on very shorter window length of the captured data from the power network. So shorter window length in the sense, shorter in the sense, less number of samples in a cycle. So in a window, that is window wise, the window length is actually deciding the accuracy of measurement. So the window length here, the number of samples acquired in a cycle or in a window is less. We need to get very less because for protection purpose and control purpose, it is necessary to give, to take action immediately. So that's why we require fast response as far as the protection and control is to be done onto the system. Therefore, shorter window length is being required. Therefore, we are not bothering about high frequency content present in the system. Therefore, no anti-aliasing filter. Anti-aliasing filter, they are nothing but low pass filter. So low pass filter not needed for this P class type of PMU. Whereas M class monitoring purpose, we are very particular about observing the dynamics present in the system. So here the window length is longer, that is the number of samples in a cycle. Our window is very, very large, near about 200, even 200 samples in a cycle, right? So therefore the operation, it needs to perform it requires to filter the high frequency content. Therefore anti-aliasing filters are required for this M class PMU, right? So that's about types of PMU. Okay, so the PDC, actually when we use this PMU are constantly delivering the phasor information about the particular point of the power network. So once the data is been captured and this data is being conveyed to the next hierarchy level, the PDC, we call that system as, it's nothing but a computer or a server which is acquiring the data, phasor data from various PMU. So the next level of this particular technology is PDC, that is phasor data concentrator. So this phasor data concentrator, they will acquire the data, phasor data from various points of the network. Okay, so that data acquired at this PDC level can be used for making some local decision. That is to perform local protection at that particular substation level. That can be used. That PDC acquired data can be used for that purpose. So it can be used, meaning that it can be used locally. And then the collection of this phasor data being given to the next hierarchy. So the supercomputer. So supercomputer in the super PDC. So super PDC may be at maybe of a regional low dispatch center. So at the regional dispatch center level, there may be other PDC, we call it a super PDC, and that super PDC will be acquiring data from different PDCs. And that can be acquired, and that data may be conveyed to the national level of operation, that is National Low Dispatch Center. So in India, National Low Dispatch Center is located at Delhi. Right? As far as our southern regional grid is concerned, our low dispatch center, SRLDC, is located at Bangalore. Right? So super PDCs would be present at all these levels, acquiring data and doing action accordingly and conveying the operational or control activities to be performed by the respective point of the network. Okay. So this is about, so far we discussed about the phasor technology, right? Synchro phasor technology. So in this slide, it shows the complete infrastructure, how it is being used, the synchro phasor technology being used with respect to the power system operation. So it is divided into 3 layers: measurement layer, I think, measurement layer, then data collection layer, and then management layer. Management layer in the sense application layer. So measurement layer, as we discussed earlier, it has been the PMU been installed there in the yard and getting information from the CTPT and converting the acquired analog signal to phasor form. And this phasor form of voltage and current signal and other additional informations which are derived from these information, phasor informations like frequency, the rate of change of frequency, then circuit breaker status. So all such informations are given in a particular data format, and through Ethernet, it has been transferred to the data collection layer. And from this data collection layer, it is been through internet, it has been given to the next level, hierarchical level. So for application purpose. So application purpose, actually the data acquired here are enormous in number. So we need to actually segregate the system. We need to segregate the signal or acquired signal. And accordingly, the segregated data needs to be conveyed to the respective path, right? So every systems may be dedicated to run certain programs like economic dispatch. And as far as this economic dispatch is concerned, the data, the complete dynamic data are not necessary, right? So like dynamics data needs to be segregated, right? But steady state, it requires only steady state data. So like that, the application wise, the data acquired at this level needs to be what? Needs to be performed with certain operation. So certain process, and we need to segregate the data like steady state data and dynamic data, and the dynamic data would be required to monitor or to perform certain control actions, right? So these are being divided and being fed to respective computers or systems. Okay, so this is about application layer. So this is how our synchrophaser technology is playing in our power network. Okay, so PMU, we actually discussed about the complete synchrophaser technology and what is the criteria used for PMU installation. So PMU is playing a vital role now, because it measures, we can able to get data like steady state data and dynamic data of the power network, right? So what is where to put this PMU in power network? So that is the question now. See, as of 2014, we just monitored, that is by trial, by just viewing the system like what? Nodes which is operating above 500 kilovolt. That is 500 kilovolt and above substations, and almost 200 kilovolt. So those substations, high level voltage, that is substations working at high level of voltage, are being selected to place PMU. And major transmission interconnections, that is the system is having like a regional interconnection point. So the regional interconnection point, so in that tie line, we're selecting that tie line because that tie line is the line which is connecting two major areas, and that needs to be what? That needs to be monitored perfectly. So such kind of interconnecting transmission lines are being selected to place this PMU, and the key generating plants which are delivering greater than 500 megawatt are also being selected, and also large wind generators, solar and storage locations. So these are all the locations where these PMUs are being placed. This is as of that 2014. But as of 2019, the remaining buses which are operating 200 kilovolt, that is nearer to 200 kilovolt. Okay, so but nowadays researchers are doing work on optimal placement of PMU, following observability as a criteria. So observability in the sense, by placing one PMU with the help of that data, the nearby data, bus data, can be extracted. That is, placing one PMU at a particular bus, it can be that data can be used because they are connected. It is connected, that particular node is connected with the nearby buses. So the buses which are connected to that node can be, that information can also be determined with the help of our KVL, KCL law, by applying that, right? So observability, with the help of that observability criteria, optimal placement of PMU, so that you can optimally place the PMU in the network at several points of the system. Okay, so maximizing observability minimizing the cost. That is the main motive of solving this particular problem, optimal placement of PMU. So 100% observability can be obtained with the help of this optimal placement of PMU. Okay. So this is actually as of 2014. So as I already said, 1300 PMUs have been deployed in US grid. And actually these are all different utilities which are present in USA. So as of 2014, more than 165 PDCs are deployed in US. And so this is about the comparison of SCADA and this with the SyncroPhaser technology. So 3 important properties have been discussed. That is the time synchronization, right? Time synchronization is possible with the help of that GPS, right? In SyncroPhaser technology, which is not available with SCADA. And the phase angle measurement, because we are converting the alternating quantity into the phasor form. Therefore, phase angle informations are available with SyncroPhaser technology, whereas SCADA is giving only RMS value of voltage and current. Right? It is not focusing the phasor measurement. It is missing with the phase angle information. And the reporting rate, the data rate, once in 4 to 6 seconds in case of SCADA technology, whereas SyncroPhaser technology, it gives even 60 frames, 60 data per second, right? So SyncroPhaser technology can provide wide area time synchronized view of power system at high reporting rate, capturing its dynamics very efficiently. So dynamics can be easily, efficiently monitored when you are following SyncroPhaser technology. And so the faster control action can be performed because monitoring of the system, perfect monitoring of the system is possible with the help of this SyncroPhaser technology. Okay, so next we'll talk about the SyncroPhaser. Okay, so there are many PMUs. PMUs are made by different manufacturers. So to achieve interoperability, it is interoperability feature. What is this interoperability? Interoperability is a characteristic of a product, this PMU product, which can be interfaced with other products without any restriction. So to achieve this interoperability feature, it is essential that all PMUs follow a common standard. So a series of IEEE standards were issued to ensure the accuracy of our SyncroPhaser measurements. The first SyncroPhaser standard was IEEE standard, that is 1344, issued in the year 1995. That included the measurement and communication specifications. So as per this measurement, as per this standard, some of manufacturers, PMU manufacturers, were tested for interoperability, and they found that their performance at off-nominal frequencies are not identical. So off-nominal frequencies, they are nothing but the harmonics, and that is apart from that fundamental frequency. There might be some other off-nominal frequency contents present in our signal. So they found that the manufacturers, they found that the interoperability, they tested for interoperability and found that their performance at off-nominal frequencies are not identical among all the manufacturers. So IEEE has given another defines another standard, IEEE C37.118, delivered in the year 2005. And this standard is actually clarifying the requirements for PMU response to off-nominal frequency inputs, whose frequency deviation is in the range of plus or minus 5 Hertz from the nominal frequency. And a very important concept of total vector error, TVE, was introduced by IEEE standard in this IEEE standard 2000, delivered in 2005, which is actually describing the accuracy of SyncroPhaser measurement. Actually, this error, this TVE, total vector error, there is error when you are making the SyncroPhaser measurements. There may be chances to get error due to magnitude or in phase or in both. So to combine both types of errors into a single measure, we go for this TVE, total vector error. Okay, so this is actually defined in this particular standard. And IEEE standard 1331 that is delivered in 1995, and these two, that is, and this one, these two did not specify the requirement for response of PMU to power system transients. So these two standards played an important role in steady state characterization of phasor measurement, not focusing on the transients. So IEEE actually approached with IEC and resulted in joint task, and they splitted this standard into two, that is 1181 and 1182, right? So, and they delivered in the year 2011. So this first part have focused, this standard have focused about the power system dynamics, the dynamic requirements. Power system dynamic requirements are been described in this first part, whereas the second part have described about the data transfer, the data format of this synchro phasor measured by the PMU. So the standard, it describes about standard for synchro phasor data transfer for power systems. And in the year 2013, it is again been revised, and it is a guide. It is a draft guide for functional, performance, and communication needs of PDCs for power system protection and control. So communication, about it talks about communication protocol. So the compatibility of the PMU with the communication protocol, so are all being described in this guide. Okay, so that's all about synchro phasor technology. We'll let us quickly get into this protection of power system, that is application of this synchro phasor technology for protection of power system. See, the protection system with phasor input, if you consider, it is actually see, this synchro phasor measurements have offered a solution to number of protection problems. Now we will see the protection systems with the phasor input, including this differential protection and adaptive out-of-step protection. See, as far as this differential protection of our transmission lines are concerned, it is an effective way to solve the protection problems of transmission lines, which are equipped with series compensation and fax devices. And due to the need to ensure the synchronization of input signals at both ends of the protected transmission line, true differential protection was not possible. That is, before applying the synchronized phasor measurement, that was not possible. So actually, when you are applying this PMU, that is, if you are connecting the PMU at the two ends of the line to be protected, at the two ends here, bus A and bus B. So if with available PMU, the synchronized measurement of the data are being, with respect to this, if suppose the differential scheme is operating, then it would be giving a correct operation. Okay, so the easy availability of synchronized measurement using GPS technology and the improvement in communication technology makes this differential protection possible to consider the true measurement, the true differential protection. Okay, so improving this line protection performance using this phasor measurement with the help of which are at remote ends of the line. Okay, so the next thing about the synchro phasor technology can be used for adaptive relaying. So what is this adaptive relaying? Adaptive relaying is a protection philosophy which permits and seeks to make adjustments in various protection functions in order to make them more tuned to prevailing power system condition. So by capturing the real-time data from the PMU for the prevailing power system conditions, all the relay settings are all being set with respect to the conditions the conditions which are being derived analytically. See, analytically, the engineers, power system engineers would be deriving analytically the value to be set by in all the relays, and with respect to that set value only, earlier our power network or the protection schemes are being operating against this this abnormal condition. Whereas this adaptive relaying, in the sense for the prevailing power system condition, the real-time data, based on that real-time data, the relay functions can be easily modified. And so accordingly the system can operate, the protection system can be operating. Okay, so that kind of adaptive relaying is possible. And then out-of-step relaying is actually, it's nothing but it's a kind of relay, it's a traditional method that minimizing the spread of cascading outage caused by loss of synchronism. So loss of synchronism means when we talk about loss of synchronism, it's not about the machine, it is also applicable to the interconnecting lines also. So the out of synchronism happens in the sense there might be some power imbalance. Based on that, the complete network of the power system needs to be islanded. So islanding is being performed, or else load shedding needs to be performed. So out of step, their operation of this out of step is actually causing either islanding or load shedding, right? So this has been performed with the help of two different functions, like out of step tripping and out of step blocking. But this out of step relaying is actually should able to distinguish fault and the power swing, stable and unstable power swing, right? So if suppose a fault is there, then corresponding relays will be operating, whereas for power swing due to the out of step condition prevailing in the system, that swing may be stable or unstable. So the relaying should be able to distinguish stable and unstable power swing, right? So that is possible with this synchrophasor technology, by accessing the synchrophasor measurement, and accordingly, if suppose decision is being made by this out of step relaying, then it is possible to distinguish the stable and unstable power swing, which are happen due to, it may be happen due to a greater loss of load, or shutting down of any of generators, like that. Major disturbances may cause such power swings. So this out of step relaying should be able to distinguish a fault and this power swing, and that too power swing in the sense stable and unstable should be distinguished by this out of step. So this is possible only when it is having accessibility with this phasor kind of measurement. Okay, and this is about, we followed this synchrophasor measurement. My PG scholar have done one work for performing this protection using PMU. So this is about one of work done by my PG scholar. So I have used PMU data for protecting the system. So synchrophasor measurement based intelligent fault identification and location of parallel transmission line has been performed here. We used ANN and ANFIS, adaptive neurophysics inference system, for protecting the system. And for ANN, we used feed forward backpropagation learning technique. So the input vector, actually, this is about the sample system. The sample system is 2 bus generator supplying power through parallel transmission line to the infinite bus. You know about infinite bus. Infinite bus is nothing but representing the grid, that is the rest of the power network. So here we connected PMU at this generator end, and this is unit transformer. And actually we generated data with fault simulated over a line, over a particular transmission line, and we changed the distance because actually it is the complete work has been done in a MATLAB. So in MATLAB we have that fault block. In that fault block, we used, if you look at this, we used this transmission lines on both ends of this fault block. We just changed the distance of these two blocks so that adjusted the distance at which the fault occurs. So we obtained near about 1,000 data. The fault data have been measured. See, look at here, this block represents the PMU, and this PMU we developed here in our lab. That is, we developed mathematically, and it has been giving the data like voltage. So the data acquired from this PMU are being assembled like this. The input vector X is having Vs of t, theta S of t, Vr of t, and theta R of t. So V, yes, the subscript S represent the sending end voltage and receiving end voltage. So they are received in a phasor form, and these data are being acquired for every simulated fault, and they are arranged as an input vector. And this input vector, we know the kind of fault and the output. The output to be received is being arranged in the Excel sheet. So that data, that is the output of the intelligent network, it classifies the transmission line fault. So it identifies, and location also. We were worked for identifying the location also, that is identifying the type of fault and called fault classification. And then we did the location. We identified the location of fault also. So for both of this, have used two different networks, ANN networks. So one is for fault detection, and one ANN being used for location, to find the location. So we run it, we tested, and we tested with the ANN also, ANFIS also, and we compared the performance. See, you can see this. So with the type of fault, LL fault, we simulated the fault at different distance, 90 kilometer, 95 kilometer, and 98 kilometer. And the estimated location is, you can see this. This is with the help of what a distance relay. This data we received it from base paper, one of base paper, and ANN and ANFIS output are given here. See, if you look at this, see at the simulation of 90 kilometer LG fault, it is identifying almost equal. That is almost 90 kilometer. So in ANFIS, we are getting 90.2. So ANFIS is outperforming here, and we determined the percentage error also. So this is one of the work which we did in GCT, and that paper been published. And this is about PMU deployment in India. This is as of 2014, but 2016, as of 2015, with the help of this URTD-SM, Unified Real-Time Dynamic State Measurement System, we have 1,950 PMUs installed in 351 substations in our Indian grid. They are feeding synchrophasor data to 29 state control centers. That is meaning that 29 PDCs at state control center, then 5 regional control center. So 5 PDCs, super PDCs were deployed in regional control centers. Then because we have 5 regional centers in Indian grid. See, still we have regional grids, 5 different regional grids for account purpose. Though they are interconnected, still they are functioning. So 5 regional control centers, 5 PDCs at regional control centers, and 2 national PDCs are being used in national control center. Okay. So see, these 2 are the people who were motivated me to get into this synchrophasor technology. He is A.G. Phadke, Indian. He is an Indian. Actually, he completed he received a B.Tech degree from IIT Kharagpur in the year 1959, and he completed his MS degree in Illinois Institute of Technology, Chicago in the year 1961. And along with Tharp, he joined in Virginia Tech University and started working with this phasar measurement unit. So he started his work on distance relaying using discrete Fourier transform. That was the basis of most commercial based relays existing now. So thank you all. See, these are the references I referred, and these are the publications by applying this synchrophasor technology to the power system. We worked in optimal placement of PMU and fault location and fault identification in a power transmission line. We worked on that. And also we did the stability analysis of Indian power grid through synchrophasor technology. In with respect to that thing also, we worked. So thank you all. So if you have any doubt, please ask me. So any doubt from participants, please unmute and you can ask me the question, or else you can post your question in a chat box.
Ma'am, Rajeshwari ma'am.
Yes, madam.
Please see the chat box, ma'am. There is a feedback about your question.
Oh, okay. I'm viewing, ma'am. I'm viewing. I'm seeing this.
Yeah.
Actually, they are not raising any question. Thank you. Thanks for your compliments. Thanks for your compliments. Yeah.
Okay, ma'am. Ma'am, thank you so much for your elaborate presentation about power system and application of SCADA, and also research work done by your research scholars, ma'am. This is more informative and a useful session, ma'am. Thank you, ma'am. Thank you, Rajeshwari, ma'am.
Thank you so much. Thanks for the given opportunity. I once again thank you. Thanks your organization for making this wonderful program. So thank you one and all present on this line. Thanks again.
Thank you, ma'am. Thank you.
One of the participants is asking for PPT. Vimala madam.
Okay, ma'am. We will share, ma'am, at the end of this.
Okay. Okay, I'll share PPT to you.
Okay, ma'am. We will post through the mail.
Okay. You can post it to the participants.
Okay.
Yeah. Thank you.
Thank
you so much.